Okay, so
yeah, so I will do a brief introduction. Okay, yeah, it's recording.
Right.
Yes.
Oh yeah, go ahead.
Okay, right.
Sorry,
Yeah. Okay. So welcome everyone to our seminar at ISEN, and today we have the great pleasure of having Clifford Johnson as a speaker. So Clifford Johnson is a professor of physics at the University of Southern California, and he's an expert on string theory. He has a very famous book on brains, on the brains, and has worked on many things on the gravity side and on the CFT side, like extended black hole thermodynamics more recently. And now he has been doing some very interesting research on the exact holography of JT gravity and its relation to some very interesting CFT models. So that is what he will be talking about today. Okay, so here we have Professor Johnson.
Well, it's a real pleasure. Thank you for the invitation, and I hope you'll be as excited as I am about some of this stuff by the time I'm done. So the title is Quantum Gravity Microstates from Fredholm Determinants, and what I'll try and tell you is a little bit of some of the techniques that I've been using to uncover some very interesting aspects of quantum gravity in this toy model supplied by JT gravity that I think are important phenomena that we dream about when we talk about quantum gravity and how it might be. This really seems to capture at least one or two of the key, maybe generalizable key phenomena that we care to see perhaps in higher dimensions. And I'll tell you about a connection, a direct connection to higher dimensions as well. Now, I don't think we're likely to fully understand all of the wonderful things that we want to understand about quantum black holes and quantum gravity more generally if we continue doing just what we usually do, which is a sort of semi-classical approach where we look at various kinds of solutions and then essentially do quantum physics around those solutions. And we've built up a wonderful story about quantum gravity, at least in a number of approaches, using that sort of approach. And we all know it's limited, but we need good models of how to go beyond that. And the point is that many of the things we've been looking at are in the back of our minds telling us that geometry, which the classical theory of gravity is based on, should be emergent in some way in the full quantum theory of gravity. But it's very difficult to construct models that where we really have control over that. We see hints of it, we see strong suggestions of it in various kinds of dualities, but being able to actually follow the geometry emerging is difficult in general. There are other approaches where you can do that to some degree, and I want to tell you how this works in this approach. So my philosophy here is that whenever we do find a model, we should really scrutinize it and try and understand everything we can about it. And so JT gravity is such an example. And I'll remind you a little bit of what Jacques Teitelbaum gravity is. And it's of interest. You may have had talks about it from other speakers. It's of interest because it connects lots of interesting areas of research. It's a model of 2D quantum gravity in its own black holes and wormholes and things like that. But it's also telling us about the low temperature quantum dynamics of high dimensional black holes. And that, I think, is a really additionally nice feature of it. So what I do want to try and get at is not just JT gravity on some manifold, but somehow go beyond that. What happens once you include all of the possible topologies you might think of, as quantum gravity would suggest that you should do, some of the topologies and geometries. Is there anything beyond that? And so that's what I will mean when I talk about non-perturbative physics. I'll be talking about non-perturbative in summing over topologies. And once you go beyond that, if there is anything beyond that, it'll be something that lies outside of our ability to describe it geometrically. So it'll be non-geometrical. Looking ahead to some of the results I'll get, I'm going to be able to compute non-perturbative corrections to various kinds of things that we know classically, get access to non-perturbative information in regimes that normally we don't have good control over in this context. So I'll be telling you how to compute, for example, these wiggles in the spectral density. The dotted line is the classical physics, and then there's some non-perturbative physics, and go even beyond just getting those wiggles, and we'll try and understand what the meaning of those wiggles are. I'll be able to compute important thermodynamic quantities such as the full free energy of the model if I can get access to this non-geometrical sector. There's also a quantity called the spectral form factor, which I might not have time to talk about, but I'll be able to compute that as well. So I should say, by the way, feel free to stop me when there are questions, if people have questions. So just to remind you very briefly, JT gravity looks something like this in Euclidean approach. Here's the action. I have some manifold M. I also boundary dm, and I have these terms, these bulk terms here, and these boundary terms here. Very, very briefly, the idea here, once it boils down to the nuts and bolts, is that I have some sort of geometry, the Einstein gravity pieces, but there's also a scalar, and the scalar is called phi. And essentially these two things work together in such a way as to capture the physics. Now, a couple of other interesting things I should mention. There's a parameter called S0, which I will in a moment remind you is actually the extremal entropy of the higher dimensional black hole that this would come from. And M can have any topology, some number of boundaries and some number of handles counted by G, boundaries counted by B. It has some Euler characteristic that looks like this. And by virtue of the fact that I have S0 times this Einstein-Hilbert plus boundary piece in this precise form, this is essentially the Euler characteristic in 2 dimensions. This counts the Euler characteristic. And so while it doesn't keep track of dynamics, it keeps track of topology. So in computing e to the minus I will have some factor that looks like this every time I do a computation on some surface.
So the role of the last 2 terms are essentially just to evaluate the Euclidean action, let's say, because it's not dynamic.
Indeed, it'll count topology. The dynamics is actually here. Now you can actually see qualitatively that because this is just linear in phi, essentially it's acting as a Lagrange multiplier. So phi, in fact, let me write, if I were to do the path integral over phi, this would just then force r equals -2. It would say that locally it is some ADS. Right. And what ends up then is that the non-trivial dynamics all ends up on the boundary of the model of the system. And that is where you then end up with a picture, which I probably haven't drawn anywhere, so let me put it here. You'll end up essentially, that would be the boundary of ADS, and then there'd be some boundary dm, which then the dynamics is basically, if I fix the length of this boundary, allow it to do whatever, take whatever geometry it wants to, including the possibility of having handles and things in the interior. So that's sort of essentially the dynamics of the model in this Euclidean presentation.
Clifford,
I'll say a little bit more on the next slide.
Clifford, what if you add dynamics to the scalar field?
Say that one more time.
Yeah, if you add dynamics to the scalar field in this case,
potential to this for the scalar, for example,
yeah,
or you mean kinetic terms?
A kinetic term.
Well, it's then a different, it's a different model then. It's essentially, you can add in potentials for the scalar and, interesting, what am I trying to say? Kinetic terms and things like that, that would take you into something that is a more general class of dilaton gravity models, not just JT. So I won't have anything interesting to say about those today. There's a large amount you can do with certain classes of scalars, as studied, for example, by Witten and Maxfield and Turiachi last year, which you can also show have some of the features that I'm going to talk a lot about, which is the matrix model description. But the general story is by no means understood. Okay, so moving on then, I'll write things as follows. So if I were to study the partition function or any quantity, I'll have, oh, sorry, let me go back to using my pointer. If I were to study the partition function or any quantity, such as I might want to compute, I will have this topological expansion, and I'll always put plus ... to say there's physics beyond that topological expansion, which we want to understand. And then, oh, I guess I did have some of this on the slide. So as I said, I end up with this picture here. When I integrate out the scalar, I have the Schwarzian boundary dynamics, as it turns out, the form of the action for this one-dimensional problem. It turns out to be the Schwarzian action built from Schwarzian derivatives, and you can solve it. And so there's a large literature. Here are some of the people who worked out some of this stuff. And I'm going to be rather incomplete with my referencing on the slides because there's a lot of people working on these things. So let me, with apologies to people I leave out, let me refer you to the more complete set of references in the papers that I've listed and will list later. So the Schwarzian on the disk, the leading order looks like this, gives this for the partition function. So indeed, there's the e to the s0 factor that you get from working on the disk. If you do the arithmetic I talked about there, that's just b equals 1, g equals 0. And if I'm at some temperature beta, which corresponds to a loop of length beta, because that's the Euclidean time periodic, then this is what I get. I can do a Laplace transform and write this in terms of a density of states instead. Just z equals some rho of e to the minus like that, and define a density of states, and it turns out that it looks like that. So we're going to come back to that shortly. Okay, so if I were to sketch it, it looks something like that. I'll sketch that again, so let me move on. The black hole picture, in case you're wondering, is something like this. I have, for example, a 4-dimensional extremal black hole. And as is probably familiar to all of you, if I were to take the near horizon limit of this when it's extremal, I end up with the geometry factorizing into an ADS2 cross S2. So that's the t equals 0 geometry. And there's some entropy there given by the area divided by 4 g Newton. And that's what I'm calling S0. The way to think about JT gravity then is, and this works for a wide class of extremal black holes and black brains of various kinds, is that if I were to come away from t equals 0, then the geometry is going to change somewhat. This ADS2 will get spoiled somewhat, and that S2 will get spoiled somewhat. And there's a scalar which keeps track of the size of that deformation, that S2. And indeed, then what I get is a picture like this, where I go at small t, then the yellow is that boundary I drew before, but it has dynamics, and that's the dynamics that the JT gravity captures. A nice way of making contact with work that is very familiar from higher dimensions is as follows. I have the entropy I can compute by simply doing the usual thermodynamic manipulations here. And what you'll see is you get the leading entropy, as I said, extremal entropy, plus a piece that's linear in T, and then a logarithmic correction with a particular coefficient. These sorts of terms are known from other approaches in higher dimensions. Well, the JT gravity captures all of those on the nose. Okay. So the landmark result, which I'm going to build on, is the fact that Shard, Schenker, and Stanford in 2019 observed something quite remarkable, which is that doing the JT path integral on any manifold M, getting the factor that I talked about before, that number you get times that factor is the same number you can get by working in a completely different model, which is a particular double-scaled large N random Hermitian matrix model, where the expansion parameter there is 1 over n, and it's 1 over n to the minus chi. So that's quite remarkable. I'm going to have to tell you a little bit more about what that particular model is, but that on its own is quite astonishing. And they showed to arbitrary orders in perturbation theory that this is true. Roughly speaking, just to remind you of why large N matrix models have anything to do with two-dimensional gravity, this is an old story. If I were to write down the partition function, I'm putting a tilde on it because it's not the partition function we were just talking about. I write the partition function for the random matrix model where it's an n by n matrix M with some potential that looks like this, something that would give you a Gaussian probability or something higher if you turned on these higher order terms. You can pretend that this is a toy field theory, and then if you were putting on your Gerard Tuft hat for a moment, you would go, well, I can expand the Feynman diagrams, and at large N, observe that the topology of the Feynman diagrams I can draw on surfaces of given topology, and they're organized by 1 over n. And so the 1 over n, this fact here goes back to the 70s. There's a 1 over n expansion of these models that correspond to the Feynman diagrams you can draw. But I can, and the Feynman diagram is this blue line here, and it's a double line because you can think of the matrix as propagating 2 indices, if you like. And so that draws these ribbon diagrams. And if I draw the dual to these ribbon diagrams, you see that, for example, if I have a cubic vertex, I have a triangle. If I have a quartic vertex, I have a quadrangle, and so on and so forth. So that surface that is dual to this thing, you can think of as a tessellation of the surface that you're drawing it on. The key point then is that as I take n goes to infinity and I tune the couplings in a particular way to what turns out to be a certain class of critical points, you will end up with surfaces that are smooth and, sorry, let me say it again. You'll end up with surfaces that have a large number of diagrams for a given fixed length. And so in the limit, end up becoming better and better smooth approximations to the large smooth surfaces that you're trying to do the path integral for. So one way of thinking about this is that the matrix model can be thought of as a way of regulating the path integral. And that's back in the late 80s, early 90s, one reason people studied matrix models. Now, the surprise, perhaps, is that this class of gravity theory had anything to do with these matrix models. And moreover, that you could show explicitly that the two were equivalent, which was also very hard to do in the early days, even for the other kinds of gravity models that we were considering. So the correspondence ends up being something like this. The path integral of the JT gravity so at some temperature beta ends up being what's in the matrix model language often called a loop operator. It's some trace exponentiated M appropriately defined in the double scaling limit. The key points, which I won't go into here because we won't really need them for what we're doing, is that you can actually show this as Triple S did, Triple S being these people, by using various beautiful mathematical results that were in the literature by Mirzakhani and Enyadarantan, which is that you can show that the topology, working on a surface of a given topology, can be, the results there can be related to surfaces on a different topology in a recursive way. And the integral you need to do to carefully make sure that you're doing the path integral and properly integrating over moduli space and counting the results properly and all of that is an important mathematical problem. And Mirzakhani showed how to relate the appropriate quantities, the actual measure on the moduli space of such surfaces and so forth. And this was cast into a form relevant for matrix models by these two authors. So what Triple S were able to do was actually show that if you start with a particular disk level result, for example, in the form of the spectral density, you can compute everything at higher order through this recursion. And so all they needed to know then was that Schwarzschild result I talked about before, and then that tells you what your result is at some higher order topology, and then you can do the completely different calculation on the matrix model side and the answers match. So it's important to realize that there are also various, I guess I get to call them variants now and be very fashionable, variants of the JT gravity model and its matrix model correspondence by Stanford and Witten, which came out a few months later. I also, a lot of the results I'm talking about today will be relevant to those too, but I won't have time to go into it. The key point here then is that this result, remarkable as it is still is still perturbative. Those authors did make some partial non-perturbative observations, but overall the key aspect of the correspondence is perturbative, and we need more than perturbation theory for the reasons I said at the beginning. Before we go any further, though, let's actually be very explicit and talk about matrix models as explicitly as one can. And the most famous prototype is the Gaussian-Newman tree ensemble. And this is so simple that you can actually do this at home with things you'll find around the kitchen or what have you. You have all the tools. All you need are, well, Hermitian matrices with Gaussian probability. What could be simpler? So there's the probability. So that's like I turned off all of those G's I had on the previous slide, and I just had that leading squared term in the potential. So that's my potential. That's my probability density. And then I just generate random matrices, and I compute, every time I generate one, compute their eigenvalues and histogram them, see what we get. And so very famously, as you may know, eventually a pattern emerges, and very quickly, even for moderately sized matrices, you'll develop what's called Wigner's semicircle law, which looks like this after some scaling, which I've done here. Now, the key point is that I can, the double scaling limit essentially is doing the same thing for arbitrary potentials, but it's zooming in on an endpoint. So I'm going to do that. I'm going to ask what's going on in the neighborhood of an endpoint of this ensemble of matrices, this often called Dyson gas of eigenvalues. And so you can see in the previous line, my endpoints are at plus or minus 2. Let me focus on minus 2, plus some small piece, which I'll call E. And there's some scalings that tell you how, as you zoom in to the endpoint, how many powers of n, as n's going to infinity, do you need in order to get to the neighborhood of those endpoint eigenvalues, and get something that either doesn't blow up in your face as n goes to infinity or go to 0. And these are the powers of n that you need. I'm including this little parameter delta here as a bookkeeping device that I may or may not use later on. But the way to think about it is that delta goes to 0 as n goes to infinity. And if you put all of this scaling into here, you'll get the root e you might expect. But I want to do more than that. So let's actually just do that explicitly with the experiment before. I can actually go ahead and do the same sampling that I did before, but scale things and then histogram. Now, had I continued, what you would see actually is that this blue stuff eventually fills up this wiggly line here. And this wiggly line is what I want to talk about next. It actually, in the case of the Airy model, has an exact form that looks like this. And indeed, this is one of the reasons it's called the Airy model once you get to this double scaling limit of the Gaussian model, because everything's built out of Airy functions. Now, the way to think about this is that I have the leading disk piece, which is essentially a root e, which is essentially this dotted line here is a square root of e, just the end of the semicircle, and then there's this structure if you look closely, and that's the non-perturbative physics. So that's the stuff that's in my ... as I usually denote it. So there are perturbative pieces, perturbative corrections. There's an infinite family of those, and then there's non-perturbative pieces. So this is a model of the kind of thing that we want to do, but not for the Airy model, which is just a toy Gaussian model, but for the full thing that corresponds to the gravity theory. So I want to dig a little bit deeper into why this is called the Airy model, because it will help me unpack an important piece of technology, which are orthogonal polynomials, which are often used to study these kinds of models. So what you can actually do with the matrix model computations is rewrite everything in terms of orthogonal polynomials that are called Pn. They're orthogonal with respect to the measure of the matrix model itself. So in general, I had some v, if you remember, e to the minus v. So that's the measure. And there's some orthogonality condition that looks like this with some coefficient there. Sometimes you divide out by that h, and then everything is orthonormal. And then the integral, this integral looks, there's a notation you might use where this then just looks like a bra and ket, and that's a delta as opposed to an h. Now, importantly, there's a recursion relation relating the different orthogonal polynomials. Essentially, they start out, Pn starts out as lambda to the n. So if I multiply by an additional lambda, I'll get some piece of the Pn plus 1, for example. This is the precise relation. Lambda times Pn looks like Pn plus 1 plus some admixture of lower order p's given by some coefficient that you need to compute. Now, in the simple case of the Hermitian case, this is actually they're just Hermite polynomials, and then there's a standard relationship between the different Hermite polynomials, and this Rn here is just n. But in general, for some arbitrary v, it's something much more complicated. It turns out you can rewrite everything so that if once I know what the orthogonal polynomials are, if I can compute the Rn's, I can essentially rewrite the whole model in terms of my knowledge of the Rn's. It's just, you can basically plug this identity back into the defining matrix integral and see that you can rewrite any matrix integral in terms of the Rn's. So the problem then is to find the Rn's. So now let's take the large n limit. The large n limit essentially is what we said before, which is zooming in on an endpoint. But in terms of these quantities, it looks like this. So first I'm going to define a variable which becomes continuous in the large n limit, little n, the index over n. I'm going to call that capital X. And then the orthogonal polynomials become functions of x. So the p sub n becomes p of x. And the Rn's become R of x. So these now become functions, which we're trying to find. And in the double scaling limit, what actually happens is that when you zoom in on the endpoint, various scaling pieces survive to define the physics that you're interested in. So as we saw before, the lambda, the scaling piece of the lambda, as I scale away from the endpoint a little bit, is what I called E. And similarly, X is at the endpoint, but then there's a little piece that scales away from it called little x. 1 over n itself picks up, it would be going to 0 in the large n limit, but it picks up a non-zero scaling piece, which I'm going to call h bar for reasons you'll see in a moment. And then the functions p, the orthogonal polynomials, become some new functions, which are called psi, and the recursion coefficients become a function called u. And that just comes from doing the algebra and scaling everything and following your nose. Now, what happens rather nicely is that the operator corresponding to inserting lambda in the matrix integral, essentially the content of this recursion relation, gives you some lambda, which if you follow the scaling limit ends up being an operator in these new functions, and it's actually a Schrodinger Hamiltonian that looks like this. And now you can see why I call h bar, because it's exactly where h bar would be if this were quantum mechanics. And indeed, this is a quantum mechanics because the orthogonal polynomials essentially build you a Hilbert space in just the right way in order to furnish you all the things you need to have a quantum mechanics. The spectral density then turns out to be integrating the square of the wave function over this range from -infinity to 0 of psi squared builds you the spectral density. This all goes back to rather old technology now coming from these papers. And this is in some ways one way of doing the double scaling limit in a nice efficient way. So in the Gaussian case, just to summarize, because this is completely general, in the Gaussian case, u turns out just to be -x. And you can kind of see that because u is, if you trace it back, u is what r used to be. And the r's in the Gaussian case are just n, and n essentially is x. So indeed, once you follow it through, it's just this linear potential. And that precise, and then this thing here, with a -x here, operating here, is this the defining function, defining equation of the Airy function. And so that's what those psi's become. Okay. Carrying on then, if you actually were to plug in that Airy function into there and do it, you get that function that I described before. And so that's the complete derivation of all of the physics of the Airy model, all the non-perturbative wiggles that we want so far. So the key, again, to emphasize is that you want to do the analogous thing for JT gravity, but you need to know something that you don't have from the SSS paper, which is you need to know what, something that explicitly tells you what the potential is. And that's what some of my work has been doing using this approach. So the Airy model isn't the theory of surfaces, but it illustrates the power of this approach. But before I go any further, let me point out something important about the non-perturbative physics. The Airy function, the Airy model, as I just described it, has a precursor of something that would be a problem, which SSS themselves already identified as going to be a problem non-perturbatively, which is that although perturbatively the spectrum starts out at equals 0 and then is positive, actually non-perturbatively you're seeing a tail, an exponentially small but nevertheless important tail of negative energy states, which in the full model, not in just the Airy model, but in the full model, which, if you like, combines an infinite family of cousins of the Airy model, generate a non-perturbative instability. And so how does that show up in this language? And this is one of the reasons why this language is extremely useful. You can see explicitly where that comes from. There is the u equals -x potential, as I described before. And there's I just solved this Schrodinger problem. There's the Airy functions. They're oscillatory far out, and then they hit the potential, and then they exponentially decay. And then I must do this integral to construct this fella here. And you can see that even when I get, even for states that have negative energy, even though I don't capture any of the oscillatory stuff in this integral, there's always going to be exponential tails leaking into this region. And so that's the origin of this stuff. Now, it becomes a problem when you have the full model in ways I don't have time to go into, but it's well known, again, as I said, from analogous stories in the 90s. But the picture that I drew and the language I'm using here immediately suggests what the cure ought to be, which is something like this. Just don't have that sector where you have these exponentially small tails. So how would you achieve that? Well, one way is that this potential comes down, and instead of going off to minus infinity like that, it actually caps off and goes to 0. So that would actually give you states that at high energy look very much like the Airy model that we had before, but at low energy they actually cross over into a slightly different behavior, and there's a lowest energy. There's a lowest energy which is U=0, which is equal 0, beyond which you do not get any more states. Now, actually, I didn't just make this up. This is actually achievable with a model, for example, of complex matrices M, where the potential is built out of M dagger M. So you can think of it as a Hermitian matrix model that's explicitly positive. And in fact, many years ago, I studied such models and recognized a couple of years ago that those things that I used to study way back in the 90s might be useful in this case. Instead of solving instead of U being minus X, which was the Airy case, you instead form the object R equals U plus X. So R equals 0 is that solution. But instead you construct this object. Now, in this simple case, if I construct this object and ask for what the solution looks like, it's precisely this thing I drew up here. More generally, as I'll talk about shortly, this equation will persist. It will be relevant for us for more complicated models and indeed the full model. And more generally, this capital R object is built out of higher derivatives of U. And in fact, it'll be a very, very highly nonlinear high order equation, but you'll see I'll still be able to solve it in regimes where we need it solved. But at the end of the day, this is the route to solving the problem. So just to emphasize, it's not like I've done some magic or just pulled this out of a hat. There's a natural wall at equal 0, if you like, that stops this, what turns out to be eigenvalue tunneling off to minus infinity. Okay, so the challenge is to extend this to full JT gravity, not just do the Airy model, which isn't really an interesting model of gravity. It's not even a model of surfaces. Before I do that, are there any questions? Okay, I'm going to assume I still have a connection and there are people there. I can see windows, so I think we're good. So just to summarize then, thank you. Just to summarize then, the picture looks like this. I need to solve this Hamiltonian problem, this Schrödinger problem. But what I need is the analog of finding the full potential, the full matrix model potential is in some sense the analog of finding this full Schrödinger potential U in the ways that I just showed you in equivalent in the toy model, as equivalent in the toy Airy model case. If I find that Hamiltonian, then I can solve it and I do this integral and that'll construct the potential. So that's my goal. So this is essentially what I did in these two papers for JT gravity. And in this paper, I did it for a bunch of supergravity models as well. Let me briefly explain how it works. One way of seeing how to proceed is as follows. So here is the disk level model, as I talked about. And if I were just to expand the spectral density in powers of E, it looks like this. There's an infinite family of powers of E. And one way of thinking about this, and so I should say that Triple S made this observation as well as Okoyama and Sakai, is that you can think of it as in some ways being some limit of some known minimal string theories that people had been studying in the 90s, put together in an interesting way. The way I like to think about it is that you turn on all of these models with particular coefficients. Now, each minimal model has a different characteristic power of E behavior. As you can see, it's basically e to the k minus a half for k equals 1, 2, 3, etc. K equals 1, that e to the half, that is the airy model, and that's sort of how it leads out. But then you get more interesting stuff. So it starts out as root e, and then it gets more interesting. And so you need to know how to add in, and in what sense you add in all of those other models. So you should add together these models, and add is a sort of sloppy term. It's not linear at all, but you combine together these models in a particular way, and that will build for you the correct thing if you use the right tools, and these are the tools we're talking about. The other thing to notice is that at leading order, the solution to the string equation, as the equation for U is called, that leading order piece, which I'll call U0, when you do essentially a WKB approximation to this, ends up looking like this. It looks like this integral that I need to do. And the picture looks like this. Essentially, I have some leading order potential U0 that looks like this. And I just do this integral. So I'm at some E. I construct this square root. I go only up to some point that this is real. And then I do this integral with some coefficient there, which is just normalization. And I follow it through, and that will build for me the leading spectral density. Why is this a nice picture? Because I can reverse this picture. I can ask, well, if I have a given spectral density, what U of X do I need in order to build that? And so at leading order, I can actually deduce the ingredients, at least at tree level, of in terms of these minimal models that I need. So I'm going to write this in this following form. I had it like this. Oftentimes people just put the minus infinity to 0, and it's understood. You just take the real part. And I'm going to just change the variables and make it a U integral instead. And there's some function there, which is just the derivative of U with respect to X inverted. That goes there, just the Jacobian for that change of variables. So I'll show you how to use this in a moment. The point is that let's look at the airy case, for example. If I know U equals minus X, then I can compute F. I can put that in there. I can do that integral, and that just gives me e to the half. It turns out that this is just the beginning of an infinite family of cases, that if they start out as minus X to some 1 over K, and I stick that in there, that integral will tell me that rho leads out as e to the K minus a half. So this tells me the characteristic feature of the minimal model that I need. It should, in perturbation theory, have this form at leading order. There'll be corrections and there'll be non-perturbative pieces, but at leading order, this is how that works. That's enough to tell me what my recipe is if I follow my nose. So in general, the full string equation, as it's called, the full nonlinear equation, is built out of an object that looks like this. In fact, for the emission matrix model, it's just this. So this R subscript K is some horrible combination of U and its derivatives. And there's some coefficients here, which you can think of as sort of couplings, the TKs, we'll call them. In the case of K equals 1, TK is just 1, and then all the others are 0, and that's the airy model. You can basically see that would just boil down to U equals minus X we had before. In general, the full equation looks something like this. So I can invert this, compute the F, put it into here, and then deduce for what F built like this, for some unknown TK, for what F will I get the Schwartzian that we know we should have at tree level? And it turns out to be that this is the recipe. And so there's a particular, so this is what I mean by saying this thing is built out of minimal models, in fact, an infinite number of them with very particular admixtures, very particular recipe, and it'll build for you this particular gravity model. Now, for the full non-perturbative definition, you need to do that recipe, but you need to use minimal models as defined by the more general equation that comes from the well-behaved complex matrix model. And so essentially R looks like this with the TKs I gave you before. These RKs are those combinations of U and its derivatives. I plug that in there, and that's some horrible equation, which actually there's infinite order formally, but it turns out you can truncate it, and the regions you can truncate it at can be placed such that they are out where the physics is classical, and you already know the answer. So I showed all of that in those papers of last year, and there's no time to go through that except to show you the results. For JT gravity, you can really do this. It's enough to solve, I think, something like a 15th order differential, nonlinear differential equation to get enough control over that potential. This is what it looks like. And indeed, you can then put that into this problem, the spectral problem, and solve for the spectrum, and that's the result. So now we see what I promised. The dotted line is that Schwartzian result, the Cinch function. And now we have non-perturbative physics. And that is a lot of what I was up to last year in a variety of papers for a variety of models. And in the last part of the talk, I'm going to tell you how to go well beyond just that. But let's for a moment just pause and see what we've got so far. So this is a full non-perturbative completion of JT gravity. Now, there's a larger discussion to be had about whether that's the only way of non-perturbatively completing JT gravity, and that's up for grabs. There are other approaches on the market coming out in recent times, but it's not clear just yet. They aren't well developed enough yet to be able to compare them to see whether they give the same answers or different answers or how they differ. So right now, it's just enough to get a non-perturbative completion that you can actually do something with and do some interesting physics with. And that's what we have through this work I've been doing. The key point here is that the results are explicit. This isn't just some formal non-perturbative definition. You can actually compute things with it. And one of the things I did last year was compute, for example, the spectral form factor, for which you need non-perturbative physics to get some of the important features. Well, I won't have time to talk about that, so I'll move on. As I said, there are various other models you can do this for which I did in these papers. Now, you can also study deformations, as I referred to earlier, which can be described in terms of matrix models as well. And Felipe Rousseau and I wrote a paper about that last year. And there's a lot more you can do there too. We're working on it. And you can also study various other kinds of JT gravity models, which have descriptions as matrix models. And Felipe Rousseau and Andy Svesco and I studied a particularly interesting one in this paper earlier this year. As I said, there are other definitions. I recommend looking in some of these other papers, essentially based on an approach suggested by SSS, but they are, as I said, not complete enough to get the kind of explicit results I can get using this approach. I should also note there's a huge literature now about connections with minimal strings and Liouville theory and so on and so forth, and the list goes on. And again, the references are in my papers. So that's all exciting, but I want to tell you a lot more. Let's see how much time I have. Good, good. There's enough time to tell you the next step, which is work of this year. So let's revisit the sampling, okay, that we were doing in the basement. But now let's color code. Let's color code maybe according to whether the eigenvalues I got when I did the listing of the eigenvalues, before I histogram, I go, is this the first, the second, or the third, etc. So that's the color coding. So I just do the same thing I did before, nothing new. Let me just do it again. And you'll see what happens is that now I get more detailed information. And in fact, you can see now something quite remarkable, which is that the statistics of the first energy level, the statistics of the second energy level, and so on and so forth, they line up with those bumps. In some ways, this is not in some ways, exactly, this is the explanation of what those wiggles in the spectral density really are that we got non-perturbatively. They really are information about the individual energy levels of the underlying random matrix model. So that's quite remarkable. And what I've done here is the airy case, because you can just do this by generating samples, because it's just Gaussian. Now I want to make a couple of observations here, because this is great for where we want to get to. There's some really nice features. For example, as I go to higher energies, these become sharper and sharper, as you can see, and they become more and more densely packed together. And so in some sense, what they do is they form a continuum as they go to large E. Large E compared to H bar is the classical limit, is where we're doing sums over manifolds, nice smooth manifolds. So that regime where these all end up clumping together and becoming a continuum is what we can think of as smooth geometry. In the other direction, however, I'll say a little bit about that in a moment. In the other direction, however, going this way, I have more individual states with more variance. I can't just lump them together and call it a continuum. I need to know the details of those individual microstates. And so what we see here in the airy model is the precursor of what I'm going to show you in a couple of slides, which is that if we can do this for a model that actually corresponds to a gravity theory, we will have captured in one model exactly what I was anticipating would be nice to have, which is a regime where we have a continuum and a regime where we have actual individual states and statistics, which are the gravity microstates, where I no longer have continuum physics, but I still have physics. I can still describe the physics, it's just not geometry anymore. So that really is the model of emergent geometry. Let's check that it all makes sense. Let's check that it fits with everything it should fit with. Recall that e to the minus S0, the H bar thing I was talking about, what I'm calling H bar, which is the 1 over n, looks like this. So if I take a log on both sides, S goes like, it's logarithmic in n. In other words, a smaller H bar, more classical, if you like, I have a larger extremal entropy, and I should have something like more states. As you saw in that little animation, I hope, let me just run it again. Here, you can see that as I dial down H bar, if I work at some fixed energy, as I dial down H bar, I have more and more microstates, and that's exactly fits with what we should have there. So let's see. And so that's nice. So our logarithms and things are all in the right place for this to work. How do we do that? How do we actually compute this? Now, if we're doing the airy model, this is actually well known. And there's a powerful tool known in the matrix model literature called the Fredholm determinant. Well, it's known more broadly than this, but it's very useful in the matrix model literature. If you have the wave functions psi, which in our case we do, it's the airy functions, you can actually compute an object called the kernel, the airy kernel, which looks like this. And what we have here, of course, is not for JT gravity. We don't have airy functions. We have these functions that I found in those previous papers for that more general potential. So now we can define also a kernel, but it's much more general and much more rich than the airy case. So JT and its variants give new classes of kernels, which, if you're interested in the mathematical physics of these kernels, probably have very interesting properties worth studying. From the point of view of gravity, we can use these kernels, we can use the Fredholm determinant to dig a little bit to get some of the things I want. Because it turns out that the kernel, and why it's a kernel is because you have some Fredholm type operator problem for which the determinant of 1 minus the kernel sorry, not the kernel, 1 minus k, where k is the operator operating on f, is of interest. This k here means the full integral operator. That's a natural object for which you want to look at its properties if you're solving this class of problem. The key point is that in the random matrix model literature, this has an interpretation. It tells you about probabilities of individual matrix model states. So the probability of not finding the first level, for example, in a given interval for the Airy problem, for example, unfortunately called E, is the determinant of this thing, evaluated as an operator on that interval. The actual probability distribution that you would normally get, normally think of in terms of, is the derivative of that. This is, if you like, a cumulative probability distribution, which is to say that if I'm far out here, then I haven't really found a level yet, so the probability is very high that I haven't found one, so this is almost 1. And as I come more and more into the typical area where they would be, it drops because I'm beginning to find them, and eventually it drops to 0 because I've more or less found all of them. So that's a way to read that. And the derivative is the usual probability function. This is a cumulative probability distribution. Okay, the key point here is that this is hard to compute. What you have to do is compute the determinant of an operator, which is infinite dimensional operator operating on this interval. And in the probability literature and the random matrix model literature, this was long thought of as something very difficult and certainly hard to do analytically, and for which there are really very few analytic results in many of the cases of interest. So what people did is they spent a lot of time trying to find equivalent ways of writing this result. The reason Tracy and Widom are famous for finding what's called the Tracy-Widom distribution, the distribution of the distribution function for the first eigenvalue of the Gaussian matrix model, is because they found a way of writing this as an equivalent problem in terms of Painlevé transcendence, and then were able to solve to show that existing solutions whose properties were known tell you everything you need to know about the F. But in general, it's hard. What actually happened in 2010, quite surprisingly recently, is that Bornemann showed that there's some very powerful techniques you can use numerically to solve these kinds of problems that end up being as good as, if not faster sometimes, than solving the Painlevé problems that everyone was excited about the couple of decades previous. So the point is that there are some techniques out there which I went and learned because we have all the tools we need. We have the equivalent of this problem for a much more complicated set of eigenvalues and eigenfunctions. But in principle, if we do this, we can actually get the individual microstate information. So just as an exercise, what I did is just to show you, you can do this problem starting with Airy functions as the wave functions, and doing this, you can, for the Airy model, here's a different way of getting what we already did by doing the sampling. And you can see the peaks I talked about explicitly. You can, once you know the first one, you can get the others recursively through a way that I don't have time to show you, but it's all explicitly doable. Now you can get these with exquisite accuracy to high levels because you know the Airy function to arbitrary precision. I will not have access to that accuracy here because we're solving very difficult numerical problems, but to my pleasure and surprise, you can actually do this to some high degree of accuracy for the first 6 or so levels, and here they are. So I give you then what deserve to be called the quantum gravity microstates explicitly. I have the actual probability distributions of each of these fellows worked out. This There's some numerical wiggling, which I smoothed a little bit, but to good accuracy, this is it. And by the correspondence we talked about before, this is in some ways also the high dimensional black hole microstates explicitly now. So let me again emphasize what we have. Going in this direction, we get to triple S's correspondence order by order in perturbation theory, where I'm using gravity and geometry to describe things. And here what we see is that those microstates have merged into continuum, and I might as well use that continuum language. As I go to lower energies, though, that's not not good anymore. And in fact, I need to go non-perturbative physics to see these peaks. And now I don't have a good geometrical description, but the matrix model is just fine. It knows about these states. These are just the matrix model states. And so I have a bad geometrical description, but I have the individual microstates. And because I have all the information about the microstates, I can compute whatever I want using these techniques. So this is the power of this Fredholm determinant technique. So I can compute explicitly interesting things. And so to end, just running a few minutes over, I apologize. To end, let me give you one of the results that I was able to put. And so all of that new stuff is in this paper here. And let me end by talking about a very important problem that bugged the community last year, which is trying to understand the quenched free energy of the model. So we need to be able to compute this thing to follow the thermodynamics down to low temperatures. The thermodynamics of the model, of the JT model, the thermodynamics of the black holes, to go back to the extremal case. If you use the usual thing that we compute, which is in fact what's called the annealed free energy, typically what we do in quantum gravity is we go, well, we compute the partition function, we take the log, and then we compute the free energy. What we're really doing is we're computing the annealed free energy. We're computing the log of the averaged partition function. What thermodynamics tells you to do really is to compute the average of the log of the partition function. And normally we don't need to worry about the difference between the two, because at high temperatures, these two things are essentially equivalent. But in this model where I need to compute, where I want to compute everything and follow down to low temperatures, I can no longer get away with the cheap trick. I need the full object. And that was something that was not possible to be done until this paper in all completion, because you can't just use geometry for the reasons I just described. You need to include wormholes, replica wormholes of various kinds, and then more non-perturbative physics. And how do you do that? And how do you keep control of that? And there are various nice results, partial results by various authors. But until now, that story was completely, was incomplete. But now I can just reverse engineer the spectral data that I have. I can compute arbitrarily Z wherever I want, because I have all the energies. I know how often they occur because I have all the statistics. So I can just go back and do that. And if you do it and compute, this is what you get. And so what you can actually see, you can actually do it and add in more and more levels. And you can see what happens at early times, it's not times, at early numbers of levels, things already settle down. The free energy starts out at 0 temperature as just the average of the first of the ground state. It's a little boy, that's about 0.66. If you go back to my previous slide and looked at that red peak, you'll see that its average is around 0.66, and then off it goes. If you use the annealed free energy, the wrong free energy, what you actually get is this curve. So you have a negative entropy, because entropy is the slope minus the slope. You have a negative entropy at some point, which doesn't have a good interpretation. So, and there you can see at high temperature, they merge. But this is the curve you get by using the new information from the Fredholm determinant. So this is a nice example of the kinds of problem you can solve if you have the full spectrum as given by this new Fredholm technology I've been using. I should probably stop. The key point here then is that the non-perturbative sector captures now we have all of this stuff, not just the wiggles, but what the wiggles mean and what's underlying the wiggles. We have the full JT gravity black hole microstates at our command. This is just an explicit illustration of what I was saying before, which is a transition from geometry to non-geometry in the matrix model, and we can see that happen before our eyes. So it's very explicit and worth studying. The key model here, the key tool that I use for all of this last stuff is the Fredholm determinant. And there's actually a way of understanding it as a D-brane probe. I could say more about that another time or in the discussion. And it's natural to wonder what other random matrix model tools might be useful from the vast random matrix literature that might be useful for studying quantum gravity, and what quantum gravity questions can we answer with this remarkable toolbox. So thank you for listening, and thank you for allowing me to run over a few minutes.
Thank you very much, Clifford, for your very nice talk. So are there any questions from the audience?
Do I have to raise my hand? Because I think somebody is raising their hand.
Let me check in the participants. I don't see any raised hands. No, yeah, there is one here. Sorry, but it doesn't tell me. Daniel, yeah, it's just you. It's just you yourself.
Maybe it was a mistake or something.
No. Hi, Daniel.
Well, hey,
go ahead, Daniel.
Nice to see you. I had some specific questions. Are those okay? Can you go back a couple of slides?
Yeah. Give me an idea of where you want me to go back to.
Yeah, I think the closest one is where you did the numerical computation of the gravity microstates.
So
I never thought I'd say that.
Yeah, there you go. Let's get used to saying that, folks. This is I find this very exciting.
Yeah. So
am I on the right slide? Am I on the correct
exactly.
Slide? Okay,
yeah,
good.
That one. I had the idea that before you said there was a numerical method to calculate such things, but I thought it was for the f function, the ones that are like dotted. And then when you showed this plot, I was surprised that you had the like kind of Gaussian colored plots. So I got confused. How did you get these?
Okay. Let me go back. A previous slide. Maybe that might be more useful. Okay. Let me jump out and go back to here. So this is the thing you compute. What you normally get. What you get more on the determinant essentially gives you the cumulative probability, which are these dotted lines here. Can you see? I don't know if you can see that.
Exactly. Well, I can see them.
Yeah. So that, and then minus the derivative of that are these peaks.
Oh.
Yeah.
Right. So you get
once I have these guys, I can just numerically compute the derivative. It's nothing.
I see. Oh, nice.
Yeah. And
my other question was a lot earlier in your talk, but right from the beginning when you were talking about topological recursion, and then you talked about actual recursion in polynomials in the Airy model, I wondered if those two were connected and if that's why the word recursion was used in both cases.
I see. No. There's two different kinds of recursion. At any order in perturbation theory, I could be working with the orthogonal polynomials, the full set, and there's a recursion relation between them. And that's different from the recursion relation that goes between topological levels, is what I mean.
Okay.
So even if I'm working on a disk, for example, a leading order, I have a full set of orthogonal polynomials, n of them, that have a recursion relation between them, even if I didn't know about, the disk with a handle, etc.
Yeah.
So, yeah, a lot of things recurring.
Okay. Thanks.
Pleasure.
So, are there any other questions by the audience?
I think maybe Maria.
Yes.
Go ahead.
I have a question. Hello.
Hi.
I would like to know if do you expect that these very nice techniques of random matrix? I'm not familiarized with. I'm familiarized with matrix model, but not with random matrix model. Can be applied for gravity, for example, in 3 or more dimensions, or one should impose some extra conditions, or it's not known. I don't know what is the state of the.
No, it's a really great question as to how much of this is going to teach us about, you know, gravity we care about. So there's a big discussion about first of all whether an analogous thing would happen in the contexts we already know, and you may already know this discussion, for example, where people are asking, well, let's go back to ADS-CFT, for example, and you know, I have ADS-5, right? So in some ways, is the matrix model the Yang-Mills theory that's supposed to be dual to this, and should I be doing some averaging there, and what is that, and is there anything to be gained by thinking of that sort of thing? And the answer, I think, is still not fully understood. Whether that generalizes in that way. There are various three-dimensional stories where you're doing various kinds of averaging, and it does seem to build the gravity theory. You may know some of this work, for example, Maloney and Witten and other authors like Jansen and Kotler and others, and some recent work by Oguri et al. Really pushing some of that. And again, that's very, very special three-dimensional story going on there. The general story, I think, is really poorly understood. I think then there's also the other matrix theory, right, which is what was called, you know, BFSS matrix theory, which, you know, may have some relevance too. I think we may end up as a community revisiting that model too. I don't have a good idea as to what the general story will look like. For me, I think the clearest and certainly still fruitful connection to higher dimensions that we have is that we know that by dimensional reduction of various near extremal things, we get JT gravity. And so this is at least maybe a little bit of a window into interesting four-dimensional physics, because these really still should be the same microstates of the higher dimensional black hole, perhaps organized in a simple way, not capturing all the dynamics, but some subsector. I think that alone is worth studying using these matrix models and capturing some of that physics. And frankly, I'm actually surprised how little the community has talked about that aspect in terms of trying to make those connections. So I think there's something to be understood there. But yes, there is this larger question as, can I just describe any gravity theory in any dimensions as some massive matrix model that I may or may not be able to compute with? And I don't know the answer.
Well, your results are really very, very nice. So it would be wonderful if that could be extended.
Thank you.
So many thanks.
So any further questions? I have a few questions myself.
Oh, great, good.
So I was wondering about the dictionary between JT gravity and matrix model, let's say. So like, okay, in the case of the matrix model, your states are like they're the eigenvalues basically of the matrix, right? Yeah. And they have this distribution, right? Right, the probability distribution, and you can think of them as like wave functions in the energy, let's say, okay. But what would they correspond to in the gravity side, basically? Like I mean, I'm a little bit wondering about the correspondence. Like, what do they map to?
So they being what in particular? The wave functions?
Right. The wave functions of the probability distribution of the eigenvalues, of the individual eigenvalues of the matrix, of the random matrix. What do they map to in the gravity side?
Good. So that is at least partially known. I'm just trying to think if I have a. Just wondering if I had made it. I actually didn't make a slide. I didn't make a slide about this, but let me just write. Let me just write here. The way there is an understanding in some sense of these wave functions here.
Mm-hmm.
I'm going to throw some words out that maybe just help you search in the literature. But from the model, there's several pieces of technology coming together in different fields. These, from a point of view of if you're a person studying the underlying integrable system, these are called Baker functions or Baker. I never know how to pronounce it, so I'm just going to say Achyzer. Yeah, functions. So these are sort of, from the point of view of some formulation of integrable systems, these are already well-known objects. And then in the early 90s, you'll find in the literature, I guess some of the earliest sort of coherent things that were said were probably by papers by Greg Moore. But then later on, I think Seiberg and various co-authors really built this up into understanding these in terms of what are called FZZT brains. So Fadeev, Zamolodchikov, Teschner, and they're a kind of D brain. So I think the answer maybe that you're looking for in terms of what physical object this might correspond to is some kind of thing that in the string theory language would be a D brain. But we're not actually doing string theory here, so they're not really D brains in that sense, but they still are somehow special kinds of boundary conditions, if you like, that the gravity theory can contain. That if this were a string theory, would be thought of as D brains. And there's certain kind of extended D brains that in I don't know how familiar you are with Liouville theory. Excuse me. The Liouville description of these kinds of minimal models, but essentially those models essentially have, as part of the target space, they have the Liouville scalar, which I will call curly phi to distinguish it from the phi we were just talking about. And you can have D brains that are either localized in that direction or extended in that direction. And these guys are the ones that are extended in that direction. So that's the best I can do in terms of giving you a sort of physical object that this thing in its entirety corresponds to. But as I remark in my paper, it is actually kind of nice. Essentially, you're building this Fredholm determinant is built out of, sandwiching together two of these things. I have Ex psi E primed of X, and I integrate over X. And this object, so it's like sandwiching together two of these D brains in this way, making this composite object. So this Fredholm operator is some kind of D brain probe in that sense, that's somehow then sensitive to the microstates of the underlying gravity model. I don't know if I answered the right question, but that's all I've got. I'm still trying to understand it myself.
Yeah, no. Thank you very much. So I will check out because I was lacking background literature on the original references, so most likely I will need to go back to that. But it is very
okay. Oh, good. Sorry,
right.
I interrupted. Yeah.
Yeah, no problem. No. So right. So and I had another question. You said that right. When you're constructing like the partition function of the JT gravity model, right? You can consider different genera, right?
Yeah.
And you show that explicitly where you have this term, the usual Ricci scalar, right? Integral over the Ricci scalar, etc. Right? So how does that get reflected in the kind of microstates that you get? Like, where can you see the genus expansion on the side of the matrix model? Because what I had in mind is that, you know, there's all these interesting developments of the last 2 years, let's say, where, for instance, when you're considering black hole evaporation, you have to add over different genus, let's say, spacetimes with higher genera, right? Like these replica wormholes and things like that. So I like, because, okay, I was wondering where can you see this explicitly, for instance, on the side of the random matrix model, or if it?
I think it's a great question. I think it's all down to essentially, if you like, the collective behavior of all of the n states, right? And so, you know, this picture I like to draw, and the analogy sorry, this is kind of the analogy I give when I give a public talk, which is, so I don't mean to insult you as real professionals, but the analogy I like to give is water, right? When we talk about the microstate description of quantum gravity, I have a good description where I have this fluid phenomenon, right? Water, it has things like wetness and things like that. There's this other description in terms of water molecules. No individual water molecule knows what wetness means or anything like that. It's just completely, doesn't make any sense to ask of a particular water molecule quantities about the fluid description. Nevertheless, they're both important ingredients of the full description of water. And so some collective, you know, the fact you have lots of these things interacting then gives me some effective description, which ends up being the fluid description, which is to say then that I shouldn't expect to be able to ask a particular microstate what it thinks of as what is topology. Okay. You see what I'm saying? Nevertheless, oh, I guess I should have deleted that stuff. Nevertheless, let me get rid of some of this stuff so I can make some sense. Oh, actually, I have some room here. Nevertheless, we do have some parts of the dictionary, right? We have the 1 over n expansion, appropriately renormalized in the double scaling limit, that corresponding to the, you know, the e to the s naught parameter that we had before. And so the I actually did have a slide on this, didn't I? And that's a minus sign. I did have a slide on this, didn't I? So why didn't I go to that instead of making a mess? Let's go back here. Yeah. So in some, so you know, this is the sharp. Oops. This is the sharp description. I have, on the one hand, I have my parameter e to the minus s naught, and the s naught was multiplying that piece in the Einstein-Hilbert action, which corresponds to topology. Yes. And I have some expansion in that. And on the matrix model side, I have 1 over n, essentially, where n is the number of the size of the matrix. And so that, you know, that's how the matrix knows about topology, but no individual microstate knows about topology. Right. Does that? I hope I answered the right question.
Yeah. I mean, the expansion in the genus, like it's like powers of 1 over n, right? The usual expansion of 1 over n. So it has to do with the matrix size, you say. It
has to do with the matrix size, and in some sense, that expansion, where I can do an expansion, that expansion is good when the matrix is large. Yes. So I have, you know, that collective effect is more significant than the fact that, you know, I'm going from individual water molecules to a glass of water. So
right.
I'll stop with the silly analogies now, but I sort of like it because it helps me remember what's going on.
Okay, so thank you very much. If there are no further questions, then I'm going to stop recording.